Hi, good morning or good afternoon, depending on where you are in the globe. So today we're doing the second of two webinars today, and this webinar is really about technologies for academia. There's quite a lot to cover, but as I say, we're kind of primarily tuned this or presenting this for academia. So if you're in academia and you're interested in electro-analytical techniques, then this is probably the right webinar for you. With that said, let me go forward because there's quite a lot to do. So I will talk about wearables today. I mean, for example, I've got a wearable microneedle technology here. This kind of technology, I mean, this particular watch format that I've got here, I've got a second model here as well, has actually had something like 20 million euros invested in it. So we do get a lot of inquiries about wearable technology from ZP, and there is technology on our website. But technology like this, where I say like this, is something I'm putting onto my wrist at the moment. It's had 20 million euros invested in it. It's got something like 50 patents behind it. And this is something that I will touch upon this afternoon. So it'll be quite quick when I talk about wearables. I'm also going to talk about what I call IVD, in vitro diagnostics. So when I talk about IVDs, if you can see my camera at the moment, I've got a new type of potentiostat in my hand. And this new type of potentiostat is working with screen printed electrodes. Now, I will primarily talk about ZP screen printed electrodes this afternoon, but if you're an academic who likes to print their own screen printed electrodes, then you're perfectly welcome to look at our design rules and actually design your own screen printed electrode for this new type of potentiostat. When I say this new type of potentiostat, it's really a cloud-enabled potentiostat. It never requires a PC or a laptop to run it. It only runs off smart devices, and it's immediately cloud enabled. So all the data that it does and all the processing that it does actually happens in the cloud. So that's something that we'll definitely be covering this afternoon: screen printed electrodes and cloud enabled potentiostats. I'll also be talking about commercialization. So I'll be talking about the entire kind of academic journey from undergraduate teaching to research to translation of academic science. For me, I think a lot of academic science really finishes at what we call TRL3. TRL3 is a kind of, you've done some work in the lab, you've got some raw data, you've got a calibration curve, and essentially, the calibration curve and the raw data makes up the body of your paper, and then the conclusion at the end says, and it works, kind of thing. Well, actually, we want to take it beyond technology readiness level number 3, because it doesn't impact when the work is left in scientific papers. And really, governments these days and European grants and US grants are all looking for you to translate your research into technologies that can otherwise be used by real people, let's say. I want to say real people. I don't mean that scientists and academics are not real people, but what I mean by that is people who are non-necessarily technical in the way that we are technical in. Let's say people, environmentalists who are interested in maybe water quality, maybe farmers who are interested in soil nutrients, maybe clinicians, doctors, nurses who are interested in a particular blood analyte. So we're going to be talking about that kind of translation slash commercialization this afternoon, but I'll also talk about how the same type of new potentiostat from ZP is able to play a role in all of these needs within academia, from education, research, and translation as well. So this won't be just a webinar with slides. We will, and for example, I've got a little so we've got a little bit of I've got a little bit of setup in front of me at the moment, so I'll just change cameras just real quick. So you'll see that, in fact, I've got a little bit of a setup here, so I will be doing some demonstrations shortly as well. So don't think this is just pure chat from me. There will be real sort of demonstrations as well. With that said, I will go back to the other camera, and so something I'm going to be talking about this afternoon is Sense It All. So Sense It All has a couple of form factors. One of the form factors, I kind of call it an IVD form factor. So if you can see my camera now, this is a kind of IVD format, in vitro diagnostic, that is, where you've kind of got a screen printed electrode that's been functionalized in some way to make it specific to an analyte. You want to run an electrochemical technique on it. That's what this potentiostat's for. And this potentiostat, by the way, is driven by the smartphone. And because it's driven by a smartphone or smart device, and the smart device is web enabled, the data just immediately goes to the cloud, and we actually process the data on the cloud. You won't realize that we're processing the data on the cloud because it's so fast when we do the demonstration later on. This technology stack, where we have a sensor, electronics, connectivity to the cloud, and then processing the cloud, we call that sensor to API. API in that context means application program interface. If you're interested in doing businesses, everything is about API these days. The whole modern world is kind of glued together. When you make a contactless payment, that's using API, etc. But it's also the same technology stack also supports the wearable technologies from Zimmer and Peacock as well. But I've got to say that wearable technologies like these smart watches, these cost something like 10 times as much to develop and take to market as an in vitro diagnostic. So you've got to be reasonable. I mean, I'm thinking about there's a company in San Diego at the moment called BioLink. They've raised in the last 4 years. They're doing microneedles, and this is a microneedle patch. This is not from BioLink. This is from Zimmer and Peacock. But they've raised something like 158 million US dollars to get where they need to be so far. And they haven't got to market yet, but just in the last 4 years, they've raised 158 million US dollars. So be really understanding of what it takes to do wearable biosensors. And that'll be something that I will also discuss this afternoon. Just for interest, if you want to do some of this, so I'm going to do a test. The test will be dictated by my phone. My phone will drive the potentiostat. The potentiostat will give the data back to my phone, and the phone will put the data on the cloud. The cloud system we have is called Julie. If you want to do some sort of testing of this hardware, this technology later on, rather, there is a cloud data management system called Julie, which you can see here, djulie.zimmerpeacock.no. This is where we're doing the storage processing of electrochemical data. You can open up a free account on Julie if you're so interested. And it works with an app that we call Sense It All. And Sense It All, when I was talking about technology readiness levels earlier on, I said, well, actually, most scientific research ends at technology readiness level number 3. One of the higher sort of tiers of technology readiness level says that your technology is deployed. And I just want to say that the app that I will be using to drive all of the experiments and tests this afternoon, that app is already deployed on the and you'll see it now on the Google Play Store and the Apple Apple App Store rather. So first of all, what you would need to do is you need to go to Julie. You need to register yourself an account. You'll use your email, and you will create a password. When you've done that, you are then able to put an app on your phone. So if you're using an Android phone, you can scan this QR code. If you're using an Apple phone, you can scan this QR code. And what it will do then is take you to the appropriate app store, and you'll be able to install an app on your phone called Sense It All. Now that Sense It All, you'll have to log into that app, but you log in using your Julie credentials. So first of all, Google Julie Zimmer and Peacock. You'll find a cloud system for receiving electrochemical data and processing electrochemical data. That's essentially our cloud database. And then when you've done that on your smart device, you can scan these QR codes, and that will then install an app. That app is essentially a conduit or a data stream. You'll be able to be gathering data via your phone and sending it to that cloud system. And all that will become apparent as I go forward, let's say this afternoon. Just want to give you a quick experiment, actually. What I'm going to do is, this is my phone. At the moment, it's running a very specific app. I'm just going to, on this phone, I might even change cameras just for a second, which I will do here. On this phone, there's actually a ability to read apps. What I'm going to do is I'm just going to click here. Now it's looking for an app. So what I'll do is, well, sorry, app, it's QR code. I just scanned the QR code, and now the QR code says, it will actually say amperometry on my phone now. What it's actually doing is every time I present a new QR code, this app can read that QR code. So I'm going to read this new QR code now. So at the moment, amperometry, I'm just going to scan this one for open circuit potentiometry. Now my phone says open circuit potentiometry. So every time, if you want to change methodologies, all I have to do, or all you have to do, is scan the QR code. So one of my favorites, impedance spectroscopy. So now this app will now do impedance spectroscopy. So for every sort of analyte you might be interested in, if you're doing an enzyme-based assay, amperometry is often done. If you're doing an ion selective electrode, then open circuit potentiometry is often done. If you're doing an immunoassay or an aptamer assay, impedance spectroscopy is a good one. If you just want a simple assay, linear sweep voltammetry is fine. I think in this day and age, you don't really need to do linear sweep voltammetry so much. I would actually suggest square wave voltammetry, which is also on this app as well. But for historical reasons, people might want linear sweep. Cyclic voltammetry, in fact, ZP does use cyclic voltammetry. So there's cyclic voltammetry now. So every time I scan a QR code, this phone reads the QR code and it essentially programs the phone to say, okay, so when I make a Bluetooth connection with that potentiostat, when I say that potentiostat, I should be specific, this potentiostat will know what to do because it's in Bluetooth connection with this phone. So in fact, it's an amazing thing in some ways because in fact, it's all essentially wireless. So that was cyclic voltammetry. And then if you are doing aptamers or antibody type assays, maybe even MIPS, molecular imprinted polymers, then square wave voltammetry. So you can see that this really is a modern cloud-enabled potentiostat because I'm not using a PC to control this. I'm not using a laptop to control this. I'm actually only controlling it from my phone, and my phone it knows what to do because of these QR codes. It then sends those commands via Bluetooth to the potentiostat. The potentiostat does the experiment. It sends the raw data back to my phone, and then my phone puts it up in the cloud. And you'll see that for real as we go along. So in fact, all these codes exist. So if you later on you try and find a cloud system online called Julie, and it's from Zimmer and Peacock, and you register an account there. If you later on then put the Sensi All app on your phone and you log into that Sensi All app using your Julie credentials, suddenly your phone is actually a conduit for data from, let's say, the Sensi All potentiostat through your phone and onto that cloud system. So it's pretty remarkable. Just want to show you that what's very, very, very different about what we're now doing with this really a brand new type of potentiostat is because we're processing the data in the cloud. If you want to turn your raw signal into something meaningful, you can process it in the cloud and you can send back to people's phones meaningful numbers. What I mean by meaningful numbers, so I'll just scan this ginger. In fact, I scan pH. So if I measure gingerol by cyclic voltammetry on this potentiostat and I send the data to the cloud, as long as I program the cloud, when I say program, it's all menu driven. As long as I program the cloud accordingly, I will then be able to convert the gingerol voltammetry into a concentration and send it back to my phone. Let me just do this one. Yeah. So here's chili, for example. So I'll run through a chili demonstration in a little bit. But just to understand, you can use this potentiostat as a potentiostat, and you can get amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, square wave voltammetry. Great. But actually, you can then go the extra step and actually convert that raw signal using a calibration that you'll have determined by doing your work in the lab. By using that calibration, you'll then be able to turn that into a concentration, and suddenly you've gone from TRL3, which is the sort of the dead end of all academic research, to TRL9, where actually you can actually start delivering this to real people whose problems you should be solving. Because I mean, the one thing about electrochemical or electro-analytical chemistry is it's a very practical science, and it can genuinely measure real things in the real world and make a global difference, either health-wise, environmentally wise, food production wise. I will just dip my toe slightly into wearable biosensors now. I used to have a lot more slides on this, but actually I realized this is wearable biosensors is a webinar in itself. So I think on the 31st of July, we have the next wearables biosensor, wearable biosensor webinar. But at ZP, we're very used to dealing with the skin. So the top layer of your skin is the epidermis. Under that, you've got the dermis, so you've got the subcutaneous. I'm sure many of you will have seen people, if you look at my camera, wearing these kind of patches on their upper arm. This is not a ZP product. This isn't an Abbott product, but this is an Abbott Freestyle Libre 2. If you look very carefully, you can see there's this little filament out here. That's a transcutaneous sensor. What it is actually an electrochemical cell. It's got working electrode on it, and it's also got reference and counter on it as well. So it's amazing that how, let's say, robust electrochemistry is. And those kind of sensors actually sit through the skin and constantly monitor. In the case of the Abbott product, it's constantly monitoring glucose by an enzymatic reaction. I mentioned BioLink earlier on, and when I was mentioning how hard wearables are, I was mentioning, the kind of money that are raised in order to do wearables. So this is also a microneedle patch, but this one's from Zimmer Peacock. Microneedles are less invasive than the transdermal sensors. I mean, this is the applicator that you use to add a CGM today. So if you've heard the term CGM or continuous glucose monitoring, this is what Abbott is now promoting, not just the diabetics, but they're also promoting it to people who are interested just in their metabolic health. But the applicator, the thing that pushes this into the skin, is quite a large device. One of the opportunities, advantages of microneedles is you don't need large applicators. If I want to get microneedles through my skin, I can use this watch strap and just tighten up the watch. And in tightening up the watch strap, it basically pulls the sensors through. Sounds ridiculous, but pulls it through my skin, and that's how we deliver the enzymatic reaction into my body. So that's how the microneedles are working. There's plenty of videos about from Zimmer and Peacock where I do mention that we've got most experience when we're measuring non-invasively. We do non-invasive. We've done some programs where we've done non-invasive in lactate and potassium analytes in sweat. And then we've also done implanted sensors as well. You will see videos from us where I show, I mean, maybe in these slides, but I think I've taken out some slides now. We actually put these sensing packages within fish. The fish are not dead. The fish are then swimming around, having their glucose measured, so they're the healthiest fish known to man. So if you're interested in wearables, there's too much to really mention in this webinar here, but on the 31st of July, 9 a.m. British Standard Time, or sorry, British Summer Time, and 4 p.m. British Summer Time, we will be doing a couple of webinars. When we do webinars, we always try and do 2 in the day, one in the morning, when I say morning, our morning in the UK, and one in the afternoon, our time, or UK time rather, because that way we can cover most of the globe. So if you're more interested in wearables, then we are now doing specific webinars on it. Otherwise, it's just too much for one webinar. So I am going to focus today on a new type of potentiostat. We call it Sense It All. I'm going to talk about the potentiostat itself. But before I do that, I'm actually going to talk about a problem. And I see a problem in the world of screen printed electrodes. I think there's a problem with the quality in screen printed electrodes that are used on the R&D market. And I think it's significantly holding back the R&D market, in fact. So you will see me, I will talk about screen printed electrodes and how I think it's actually causing a problem for the R&D market. Not because the technology is bad, but actually I think there's a problem with quality. So let me discuss that. Before I do that, I do want to say that, in fact, I do have some glucose strips here. The thing is about screen printed electrodes is if you're trying to develop a low cost analytical assay, can I call it that? That can be used by normal people in the normal world, then the glucose strip and the glucose meter has really demonstrated the power of electrochemistry. The fact that this little amperometer is sold in pharmacies. You've got these strips. These strips are produced at something like 5 cents each. They've really shown you that actually electrochemistry as a technology is a really good one for actually translating science out of the laboratory and into the real world. And so the glucose strip is a kind of grandfather of electrochemical biosensors. Now, it's not just glucose. I mean, if you look at a company called Radiometer, these guys are in just north of Copenhagen in Denmark. Radiometer do what's called the comprehensive metabolic blood panel. They test hematocrit, hemoglobin, lactate, glucose, oxygen, CO2, pH. They test the whole sodium, potassium, probably ALT, AST. They test a whole host of analytes in the blood, and they do it using A, electrochemistry, and B, they're using thick film printed or screen printed electrodes. Basically, they're using the same manufacturing technique that we would use to produce these screen printed electrodes. So there is nothing wrong in the idea that you are a scientist and you want to do some science that's going to impact the world, and you're probably going to measure some sort of chemical or biological parameter. And electrochemistry is a good technique, and it's proven itself to be viable and get itself out of the lab. The main problem we actually have at the moment is that because a glucose strip, to buy a glucose strip at a pharmacy will cost you 50 cents each, even though to manufacture them now probably costs about 5 cents each. There's therefore an expectation of how low cost screen printed electrodes can be. And therefore, if you look on the R&D market, there's plenty of vendors and you can find these things at quite low price. Good. That's good for you. But actually, the problem is that the people are not telling you that they're actually at low quality as well. Now, you could do a visual inspection. So I'll grab a sheet of screen printed electrodes. Yeah, they look great, and these actually are good ones. But a visual inspection doesn't really tell you about the electrochemical performance of screen printed electrodes. You only really know that when you actually start using them. So visually, lots of these screen printed electrodes look completely good. Sometimes they look terrible. If they look terrible, just don't use them. They're not going. If it looks bad, it is going to be bad. But most of sometimes the kind of quality issues with them are actually hidden from the sight as such. No, they're not being hidden. It's just not apparent by eye. The problem that we've got is that there's more choice in the world of. So you're a scientist, you want to order some screen printed electrodes. There's more choice than there is actually demand. So there's more people trying to give you a screen printed electrode than there are actually people asking for screen printed electrodes. So there's actually an oversupply both in screen printed electrodes and an oversupply in services to provide customized screen printed electrodes. So I will talk about these two things this afternoon. See, people want quality, and in most industries, it's kind of the luxury industry. If people want quality, then they pay a high price. In the defense industry, they really need technology to work every time because it's essentially life or death. So there, the military will pay a high price in order to have reliability or high quality. Now, in the world of academic research, in fact, you need quality because you're trying to do objective, quantitative measurements. But in fact, the budgets are not there to have a high price. So if you actually want high quality and a low price, there's only one way of doing it, and it's called high volume manufacturing. I mean, I use this as an analogy, but this phone, you can find phones like this for something like $250, €250 online. Now, the reason I bring that up is because it's the only reason you can get such a crazy good device for such a low cost is because it's actually got high volume manufacturing. But let's talk about high volume manufacturing when it comes to screen printed electrodes. So when I talk about screen printed electrodes, you're going to do some research in the lab. You've got your typical vendor and you contact them. I'm sure they'll send you, 75 screen printed electrodes, etc. But what they're not telling you actually is that there's a lot of people manufacturing screen printed electrodes, and conflict of interest notification from me to you now. We're one of them, by the way. We're part of this problem. So notification, ZP is part of the problem. We are one of the manufacturers of screen printed electrodes, but we actually recognize the problem. I'm going to report it today, and B, tell you how we're fixing it. So there's a problem with choice. The problem is there's so many vendors out there all competing for your business, that in fact there's more choice than there is demand, and that more choice than demand affects quality, and nobody's really talking about it. And some of these vendors on occasions disappear because in fact it's quite a competitive market. Why? Because there's so many vendors. And then you've also got and each one of these vendors, for example, and ZP has been guilty of this as well. Each one of these vendors is producing something like 50 screen printed electrodes. If you go to your favorite screen printed electrode vendor and look at their website, you'll find more than 50 screen printed electrodes. What does this mean? And also you then have academics who are also will have a screen printer, and they're also producing screen printed electrodes. So you've got vendors and academics all producing screen printed electrodes. And let's think about this. If there's only 10 vendors in the entire world, and there are more than 10 vendors, or 10 commercial companies making screen printed electrodes, and in fact, they're all producing 50 plus designs. What does that mean? It means that you've got a choice of over 500 products on that market. So all you want to do is make a measurement. It's just an electrochemical measurement. But in fact, there's 500 different types of, at least 500 different types of screen printed electrodes out there. But I think this is a very finite market. So let's talk about, when I say finite market, what do I mean by that? Imagine yourself or your colleagues in the lab and you're going to do an electrochemical experiment. So that electrochemical experiment would be taking something like a potentiostat like this, not this one because you probably don't have it at the moment, but you take a screen printed electrode, you put the screen printed electrode into that device, you put the solution onto the electrode and you run it. So how many of those experiments are happening per annum? So you could think about yourself, or you can have a look at your colleagues. You can even ask your colleagues. There's only a finite number of labs in this world doing these kind of experiments, and actually it's quite labor intensive. It's not like we're running large amounts of robotics on this kind of stuff. So in fact, it's mostly manual. I would strongly argue that there's only 1 million screen printed electrode experiments or experiments per year involved in screen printed electrodes per annum. So total market size per annum is 1 million screen printed electrodes. I did say earlier on that there are probably 10 vendors all producing more than 50 products. So there's actually something like 500 products. So you've got a total volume of screen printed electrodes required in this world of 1 million per annum. But in fact, it's fed by 10 vendors with 500 plus products on the market. If you just naively say, okay, well, those 1 million screen printed electrodes are evenly shared across all those vendors and all those products, then that means that, I know it's naive, but these are called back of the envelope calculations, and they're not to be dismissed back in the envelope calculations. They're pretty good at getting you within an order of magnitude, a true picture of what's going on in this world. So 1 million screen printed electrodes are required. Your colleagues and yourself are probably only using 1 million across the entire globe. And in fact, that means it only requires 2,000 screen printed electrodes from each one of these products. So this sheet here, this sheet has 300 screen printed electrodes on it. So that means that if I want to fulfill my theoretical total requirement for screen printed electrodes per annum, I only need 7 sheets of that. I need 7 sheets with the 300 on here. That's 2,100. So I'm just doing some quick rounded calculations. So understand that what's happening here is you've got lots of vendors with lots of products feeding a very finite market. And what they're doing is actually they only need 7 sheets. When you produce 7 sheets by screen printed electrodes, that's not manufacturing. That's super, super low manufacturing. You would waste more sheets actually setting up the machines than you would actually be producing. So that is the problem, that you've got high volume manufacturing, because there's basically a hypothesis out there, and the hypothesis, starting again, is this. Here's an electrochemical biosensor for glucose measurement. It's low cost, but it's produced in high volume. And because it's produced in high volume, it's of high quality. Glucose strips like this are actually produced in the billions per annum. Why? Because there's hundreds of millions of diabetics who are requiring billions of strips. So the high volume is what's driving it. In the world of R&D, there's tens of thousands of people doing this kind of research, and they only require 1 million screen printed electrodes per year, which means then that you've got a very finite market fed by a lot of vendors. None of the vendors are really producing a high volume. And if you have an expectation of low price, which they are meeting, but yet it's actually low volume, you actually end up with low quality. So SPEs are really being manufactured and left on the shelf to age. And it's only high volume that can drive low prices and high quality. Now at ZP, we're trying to fix this, because at the moment, really what's happening is you've actually got a good price. These things are not super expensive, but actually you've got a low quality. And I'm going to talk about quality metrics in a minute. I'm going to say that people are using the wrong quality metrics when it comes to screen printed electrodes. The question you should always ask is, what's the reproducibility of that screen printed electrode? In fact, I never get that question. So price versus quality. What we want to do is shift this graph actually and say, we are giving a better quality at the same price as everyone else, but how are we doing it? It wasn't rocket science. I just laid it out. We're actually doing it by doing what I would call high volume manufacturing. So even though we at ZP, you can find something like 50 products on our website, actually, when people come to us now, I say, look, there's a problem in the world. There's too much selection being offered. If you really want to use a carbon electrode, use our carbon 501. If you want to use a platinum electrode, use our platinum 501. If you want a very low carbon, use our hyper value carbon, or low, when I say low carbon, I should say low cost carbon. When I say if you want to do platinum, we've got a platinum low cost one, and we got a gold. One thing I want to say is just in passing is most people who are working with screen printed electrodes, if they're writing papers or writing grant applications, the one thing they put in there is, oh, I'm trying to develop a low cost sensor. Good. And then they go and use gold. Gold as a working electrode or as a material is 28,000 times more expensive than carbon. So if you've got this dream of A, commercialization, and B, providing sensors, to sort of centers in the world that don't necessarily have the kind of money that people do in other parts of the world, don't use gold. Now, I know why I use gold, because actually it's very easy to form self-assembled monolayers. But there are other ways of using carbon. You can use what's called pyrene NHS, and that will also allow you to couple things like antibodies and aptamers to carbon rather than gold. So I'm trying to make a bit of a point. Be very careful with gold. I do webinars once a week, so if you've got any more technical questions that I don't really cover in this webinar, just contact us. But just to say, if you really want to produce low-cost biosensors that are commercially viable, start using carbon. Now at ZP, we are actually able to produce these screen printed electrodes at high quality, and I'll talk about the quality in a minute, and at a low price. Some of them are much less than, well, not much less than 10% less than €1, 90 cents each. But the only reason we're able to do this is actually because rather than saying to everyone, people say, yes, I would like you to do me or rather, I'd like this particular carbon electrode. I explain to people very carefully, look, the only reason I'm trying to promote this particular electrode is because the more people that use this electrode, the higher our volume. The higher our volume, that keeps the price low and keeps the quality high. So it's the only reason that at ZP we take a very different, position on screen printed electrodes. Too many vendors saying, yeah, sure, what do you want? It's not really doing anyone any favors. I think we're actually looking at the wrong metric when it comes to screen printed electrodes. So a few years ago, this was sort of pre-2019, I was talking to an academic, and they were really interested in, first of all, they were interested in what's my peak height versus scan rate. Anyone who's interested in cyclophotometry, who's done cyclophotometry, knows that there's the Randall-Sevich equation, which kind of says that the peak height of a cyclophotomegram for something like ferricyanide or ferrocyanide is proportional to the square root of scan rate. And of course, ZP screen printed electrodes show a nice linear response. That linear response doesn't say that much about the carbon electrodes, actually. What it does say is says a lot about the diffusional properties of ferriferrocyanide. So it's even asking the wrong question. It's asking more about ferriferrocyanide than it is the carbon electrodes. They're also asking, what's your peak-to-peak separation? So if I did the cyclophotometry of ferrocyanide, theoretically, at low scan rates, I should have 59 millivolts because it's a 1 electron oxidation reduction. And people get very obsessed with that. And I've helped companies where actually they were being challenged because their peak-to-peak separation wasn't 59 millivolts. And I said, but what is it about 59 millivolts that's, does that stop you going to market? And the answer is no, it doesn't stop you going to market. For example, at ZP, we make a good carbon electrode, but our peak-to-peak separation, for example, is 67.5 millivolts. But we go to market with these screen printed electrodes all the time because we understand that it's nuancy and behavior to have a peak-to-peak separation of 59 millivolts, but it's not what's stopping you go from TRL3 to TRL9. The obsession over peak-to-peak separation is what's holding you at TRL3. But once you actually understand, so what? I didn't get my nuancy and separation, but does it actually stop me going forward and making a useful assay? The answer is no, it does not. And I think people are basically looking at this the wrong way. The metric you should be really interested in is reproducibility. If you come to, there's a website out there called FoodSense. FoodSense is a system for measuring food ingredients. It is from Zimmer Peacock. So if you ever Google Zimmer Peacock and FoodSense, you will find that. We also hold webinars, just strictly speaking, around that product. If you ever see one of our videos or see one of our webinars, you will see us take a sample, put a sample on the sensor, get a result, bang, we're done. It's a simple assay. There's no calibration. How many scientific papers do you read in the biosensor space where they're doing some sort of normalization of the data, or they've done some sort of calibration, or in fact, if they don't do normalization, they don't do calibration, what they've actually done is done a lot of data rejection, they call them outliers, But what they're trying to really solve is whether they're doing normalization, calibration, or data rejection. The problem they're trying to solve is the underlying screen printed electrodes are irreproducible. But when you're making real products, you can't do data rejection. Data rejection, the customer's going to see it. That's not the luxury we have. So if you watch one of our webinars, you'll see that there's no calibration. In this video, the engineer will just put the sample on the sensor and get a result. No calibration means simpler assays. There's nothing worse than people are saying, I want to make a low cost sensor that can be used by non-specialists. Oh, by the way, there's a calibration step. Immediately you're adding cost and complexity. But the problem you're trying to solve is that actually that screen printed electrode is not reproducible. That's not a problem with the screen printed electrode. That's a problem with the manufacturing of that screen printed electrodes. If you have simpler assays, they are easier to commercialize. I'm looking at not a company, but a group in France at the moment. They're making a sensor for measuring. I think they're doing the purification of water, and they're putting sort of disinfectants. It's a very easy assay actually, and if that assay went onto this platform, we could commercialize it really quickly for them. It's easier to commercialize when assays are simple. For assays to be simple, you can't have things like calibration on there. Why do you have calibration? Well, sometimes it's because actually the screen printed electrodes are irreproducible. It's not a fundamental thing, it's just a manufacturing thing, if I can put it that way. And if it's easier to commercialize, then you can argue impact. Impact is good. Impact allows a professor to argue what they're doing is relevant to society. Impact is good for future entrepreneurs because it generates something really important called money. So impact is important. We should all be aiming in the world of electro-analytical science to put products on the market that people can use. So reproducibility for me is the real metric in screen printed electrodes that nobody's really talking about. But at Zimmer & Peacock, we start off with a strategy, which is we do have a lot of screen printed electrodes. But if you ever reach out to me, and I will sort of immediately advise you, don't go onto these screen printed electrodes. Why? Because I can guarantee you that they're going to be good quality. Why? Because we do them in high volume. And people say, oh, I really want this one. I say, look, I'm straight with people about, the problem that we've got going on. So we will produce, hundreds of these sheets, let's say, of screen printed electrodes, but we won't just produce them in high volume. We'll also test them in high volume as well. Make sure that actually the screen printed electrodes are reproducible. So we'll take a sheet, we'll sacrifice some of the electrodes on that sheet to make sure that that sheet has screen printed electrodes that are reproducible. Take another sheet, make sure that the electrodes are reproducible. Take another sheet, make sure the sheets are reproducible. By the way, we upload all of our data to Julie. Julie was something that I mentioned at the very beginning of this, because Julie actually has the ability to crunch our data automatically for us and report things like peak height to us. In fact, you'll see that during this webinar today. And so we look at sheets and we make sure that the peak heights, for example, for the oxidation of ferrocyanide, are consistent, and we make sure that the standard deviation, the peak to peak, for different electrodes on the same sheet, that when they're tested, they actually give the same peak height. And we check the relative standard deviation, i.e., if we're going to test 10 electrodes on a sheet, what's the difference between those peak heights for those 10 electrodes? Because we understand that for an electrochemical sensor for a screen printed electrode to make sense in an assay, you've got to have better than 10% relative standard deviation for that assay to actually be commercially useful. And so we find out our relative standard deviations. We test lots of sheets, and not just one sheet, but sheets throughout the run, and we test them for peak height and their relative standard deviation. And at the end of it, we make sure that everything is within expectation and that we don't have any grossly bad sheets. And you can't do this by visual inspection. You can only do this by having high throughput testing. I think we're the only facility that actually has the Julie database. You can find the Julie database online. So things like peak height and relative standard deviation. Reproducibility is the real metric. Reproducibility means no calibration. It actually means more efficient time in the lab because you're spending less time just tossing data because of the electrode. It means no calibration. It means easier assays. Easier assays means it's easier for you to have an impact and even go on to commercialize. So here we've got several cycle voltammograms. There's something like 18 screen printed electrodes in this data set. Each one of these colors is a representation of concentration. So we're changing the concentration. And don't worry if you're joining late this afternoon, by the way, there's no big issue. We are recording and I'll send you a video afterwards anyway. So each one of these amazing screen printed electrodes, there's 18 of them in this data set. They're being tested at different concentrations. And you can see that, in fact, we have a very strong signal and a very small RSD, relative standard deviation. This is because we spend so much effort producing in high volume so that we can have a low price but a high quality. And that's why we always try to encourage people onto these particular screen printed electrodes, because then this you can quickly do a calibration curve. You didn't waste time trying to do calibration or trying to do rejection of data because you said it was an outlier. We have actually very few outliers in our when we do development at Zimmer Peacock. Why? Because we try to make a very reproducible screen printed electrode. So I think that the metric is wrong when it comes to screen printed electrodes. The only metric you should really care about, you don't want high impedance carbon. So I can understand, it is good to see the cycle voltammogram, make sure that it's not overly distorted. But the real metric that you should really care about is actually reproducibility. Because if you don't have reproducibility, then you'll end up doing in situ calibration. It's an absolute disaster. If you are going to use screen printed electrodes from Zimmer Peacock and you're not using our potentiostat, it's really important that you do have good connection with them. So this potentiostat is pretty neat. In fact, I think it's the only potentiostat in the world where there's no slot, and God forbid it, there's no cabling. I'm just going to grab some cables here. If you want to stay at TRL3, having cables is a great way of staying at TRL3, because outside of the lab, nobody really knows what to do with cables. So when we made this potentiostat, there's no slots. Because the one thing about slots is when you have a slot on a potentiostat, what it leads to ingression of liquid. And the ingression of liquid, in the lab, you may be okay, but as soon as you give that to a nurse or a doctor and you ask them to prepare a sample on there, I can promise you there's going to get some liquid and it's going to go in the potentiostat and it's all over for you. So no slots, no cables. It's a very new type of potentiostat. But that said, if you are using our screen printed electrodes and you are using a more traditional potentiostat, then please get one of the connectors from Zimmer Peacock so that you don't suffer high impedance measurements. I've seen people try to crocodile clip onto screen printed electrodes. Don't do it. Please get one of our connectors. And if you're not sure, of course, my contact details will be at the end of this webinar anyway. The other thing that happens quite a lot is electrode customization. People will request, oh, I need a customized electrode. I can absolutely assure you don't really need a customized electrode. If you want to challenge me on that, then reach out to me and I'll do a webinar on it. There's a problem with customization. People will come to us and say, oh, I want two working electrodes, one because I'm going to have an enzyme on it, and one because I'm not going to have an enzyme. I'm going to look at the difference in signal. That often comes about because actually people don't realize it, but the problems that they're suffering from is the irreproducibility of the underlying screen printed electrode. So they think, oh, to solve that, I need to make a background measurement so I can subtract the background measurement. It sounds so elegant. Honestly, in practice, I can spend a good 20 minutes saying it doesn't work that well. If you want a lesson from history, Dexcom used to do this on one of their CGM sensors. One of their continuous glucose monitoring. They used to have two sensors, one with and one without enzyme. They don't do it anymore. They learned their lessons. We do get lots of requests for making arrays like this. If you want an array like this, reach out to me and I'll talk to you about manufacturing yield when it comes to arrays. This was an array that we were requested to make. We quoted on it. We didn't get the quote because we were too expensive, but I'll talk about the lesson. This company went into liquidation. It was in part because they had an expectation that screen printed electrodes should be high quality, low cost, but they only had low volume. And because they only had low volume, they ended up paying a low price. They ended up with low quality. They had a low volume and they went bankrupt. And I'll talk about it just in passing now. The other big thing that people think they really need is interdigitated electrodes. I'll talk about interdigitated electrodes a lot. When people are doing impedance measurements of conductivity, there's lots of literature. Oh yeah, use interdigitated electrodes. You know what? It makes very little difference, in fact. Now, the true cost when you request a customized screen printed electrode is this. You want it at low cost. It's the same point as earlier on. Everyone has an expectation of low cost because of the glucose strip. These are low cost, but they're produced in high volume. But in fact, you don't have high volume because, in fact, you're either in academia or you're in a startup. So in fact, we probably need no more than 7 sheets like this, in fact. So that's completely low volume. So you have you have an expectation of low cost, you have actually low volume. And in fact, you end up with low quality. But the vendors are not going to tell you that you're going to end up with low quality, but in fact, you are going to end up with low quality. Now, in this particular case, this company was they went for their lowest cost vendor. They got a low cost product, and then they ended up actually hiring people in their quality system only to screen the incoming electrodes and to actually reject 2/3 of the electrodes they received. So they were paying, let's say, a low cost for that screen printed electrode, but in fact, they were not getting what we call a high yield. And in fact, they were paying for that low yield by actually having people just pay to just keep on testing and testing and testing. So they paid for it really through having to hire people just to do testing all the time. And then in the end, it led to their bankruptcy because they couldn't go to market properly. I did mention interdigitated electrodes a lot. Interdigitated electrodes are used by people who want to do impedance measurements because they're making some sort of immunosensor, they want to do a conductivity measurement. You find that actually when you're dealing with screen printed electrodes like this, these screen printed electrodes, quite small electrodes, very small gaps between the electrodes, and we're testing in quite high conductivity of solution. So the fact that the gaps are small, the fact that the electrodes are small, and the fact that the solutions are high conductivity means that you don't suffer things like IR drop so much in these very millimeter scale, microliter volume experiments. So people think that they need interdigitated electrodes or some customized electrode. We measure conductivity of a solution on rectangular electrodes, spiral electrodes, and also electrodes that actually were parallel to one another in terms of two platinum plates facing each other. And you know what? It all gave the same data. There's a lot of obsession on, electrogeometry and what's the best electrogeometry. When your electrodes are small, your gaps between electrodes are also small, and your solutions are quite highly conductive, such as blood, urine, buffers, tear film. It doesn't matter about electrogeometry so much. You're really not that sensitive to it. We think that, in fact, you should actually spend most of your time doing what the real value add. So I was in California years ago, and I worked there, and a very senior guy said to me, look, the only thing that really matters is actually the assay. It's not the electronics, it's not the mechanical, it's actually just the assay. So the best thing you can do in the lab is get yourself a good screen printed electrode. I'm biased, I have to put that out there, but of course I would want them to be ours. And then work on what you're actually going to do on that working electrode. What is that electrochemical assay? Is it a MIP? Is it an enzyme? Is it an aptamer? Is it an antibody? That's where you're adding the value. When you're actually doing that assay, you're adding value by how am I going to get that assay to actually work? Is it square wave voltammetry? Is it impedance spectroscopy? That's adding value. These are the hard things that most people can't do. So you should be focusing on those things. You should be testing. You should be gathering your calibration curve, first of all, in buffer, but don't spend so much time doing it. Start testing it in real samples. People say, oh, well, I can't do blood. Well, you can do blood. You can use animal blood. You can get blood from, I don't want to encourage you to do things, you've got to stay ethical, etc. But test in real samples. So, for example, if you're testing a creatinine sensor for measuring creatinine in urine, urine can be obtained, test in the real matrix. So it's really assay, method, and calibration routine are the 3 places where you actually add the most value. And then you can start thinking about potentially having commercialization. I want to talk about commercialization now. I want to talk about the Valley of Death. I don't know if you've heard of the Valley of Death. This is not just Death Valley in the US. This is a thing. You've got these technology readiness levels. When you first have an idea, that's technology readiness level number 1. When your product's been on the market for 20 years, it's at technology readiness level number 9. How do we narrow the gap between TRL1 and TRL9? So most scientific papers, they'll use large potentiostats like this. So we just grab one. Well, not most. I mean, people are using smaller potentiostats these days. They're either using potentiostats like this, and the problem with the potentiostats of this scale when you're doing electro-analytical chemistry is it leaves you or your colleagues with the impression that that's what electro-analytical chemistry is. And it almost holds you up because it's very hard to imagine how I'm going to go from this to something that looks like this. So when I say like this, I'm just grabbing it. See, this is actually a potentiostat, but it's very easy for you to imagine that this is easier to give to a doctor or a nurse than to try and actually translate this guy. Assays that come off this guy, it's very hard to imagine how you're ever going to get those onto the market. So I'm going to talk about that a little bit. There's another problem with potentiostats as well, is that even if they are smaller, they're often cabled, and the cables really, they confuse you, they'll definitely confuse new members, colleagues, and they'll definitely confuse anyone you're trying to work with outside of the world of electrochemistry. So the problem that's holding a lot of research back is actually the instruments that we're using. Now, you want to make an impact. I think all of us actually want our science to actually affect the world. And it can affect the world. But the problem we've got is that to make it commercial, most of the time, actually, governments really struggle. Because governments are very interested in the translation of science. SBIR grants in the US exist just purely to kind of translate science. But if we're going to translate the science, let's stop using instruments that look like R&D instruments. So there's, this valley of death thing where, you're at TRL 3, but actually you want to get to TRL 9, let's say, and it's quite a big chasm. But that chasm suddenly starts disappearing when the instrument upon which you're developing is the same instrument upon which you could actually commercialize or which you could actually release, I want to say, to the real world. So if we stop using the large instruments or the cabled instruments and actually start using something that, when I hold this up, this, I think I would argue that this is much more like I say an Apple product, and somebody said it looks like a flip phone the other day. So I think I'd rather be using this because this is much more closer to something that you could imagine giving to real world people. So we're physically closing the gap between what you would do in the lab and what you would actually do outside of the lab. And I'll do a little bit of a demo for you on that shortly. So we also want this technology stack to get into teaching as well, because I think that when you teach on large potentiostats or cabled potentiostats, it A, confuses students, and B, doesn't inspire them that what they're getting involved is a very cool science. And actually, it can generally, they could, within their working life, actually develop assays that could get into the real world. I mean, this is a teaching tool from a Zimmer Peacock as well, but this is the potentiostat. These are the screen printed electrodes. The whole thing, as I say, is driven off my smart device. So when you're in the teaching lab, you don't have to be even providing the laptop or the PC. They can just use their phone. And it talks to the cloud automatically as well. I realize we're getting pretty close to the hour, so I'll go a bit quicker now. So I would describe this new type of potentiostat as relevant. It's up to date, and it's really ready for the kind of lab practicals. And so we do see it as playing both a part in undergraduate teaching, in research, and in impacting, i.e. helping people get their technology off the market. And we're trying to encourage a move away from sort of potentiostats that leave people with the impression that electroanalytical chemistry is glass beakers with glassy carbon electrodes in there and, God forbid, saturated calomel electrodes, but let's say silver chloride electrodes and platinum gauze. That's not modern electroanalytical science, in fact. And so we're trying to encourage people away from that. We're trying to make it modern, relevant, a modern, relevant experience, if I can put it that way. So in order to follow this demo, you'll need a Julie account. So you can register on Julie, it's free. You can install the Sensi All app. If you rewind the recording I send you later on, you'll find the Sensi All apps out there as well. You can scan these different QR codes once you've got the Sensi All app A, installed, and B, you've logged into it using your Julie credentials, and then you can just try out all these different methods. And actually, these methods can also then very quickly become analytes as well. So I'm going to talk, and I also wanted to finish with this, that you see this QR code here. This QR code here, if you scan it, it will allow you to actually rebrand this app to not say Sense It All, not to say Zimmer and Peacock, not to have our colors. You can actually make your own apps. And so suddenly, you know, whatever university you're at or whatever startup you're at, you've suddenly gone from TRL3 to having your own app and getting yourself much higher at the technology readiness level. So this whole technology stack is for education, research, and for getting people out of the lab and into the real world, including to commercialization as well. And then we also do a pack of like 10 Sense It Alls so that people can actually use it in the teaching lab as well, because we appreciate the price point means that people can actually purchase 10 of these as well. We've actually got this potentiostat at a low price, and the reason being is because in fact we're able to produce it in high volume. So at ZP, I think we have one of the best understandings of volume, price, and quality. So I want to do a quick demonstration for you. So what I'm going to do now is I'm just going to stop sharing that for a second. I'm just going to change my camera to this camera. You can probably see my phone here. You can see. So let's just pretend I haven't said anything for the last 50 or 55 minutes. So what I have here is a potentiostat. It's called Sense It All. It works with sensors and screen printed electrodes from Zimmer and Peacock. Let's take, for example, a screen printed electrode from Zimmer and Peacock. Let's put it on there. Let's take advantage of one of the things that electrochemistry is really quite good at. I'm going to take 50 microliters of a sample and I'm going to put it on that sensor. Here I go. That's the beautiful thing about electrochemistry as well, by the way, that it's one of the lowest, it has a very low volume requirement or sample requirement. What I will now do is I'm just going to label up my data. Why am I labeling up my data? Because in fact, when I run this experiment, this data is going to go straight to the cloud, and I want to show you that it's actually up in the cloud. So what I will do is go to assay, start measurement, and off it goes. Today, I didn't talk too much about user experience, but what's really important is to see that this, as I sit here now, you may see the tip of my finger flashing. It's because there's an LED on the front of this potentiostat. This LED is telling me that this assay is running. I can also see the assay is running on my phone because, in fact, I have a status bar here. So at the same time, I'm also logging into the cloud as well. So in fact, it's now done upload complete. And in fact, let me just have a quick look. So it said upload complete. I'm opening the cloud now. So let me just share my screen. In fact, there it is. So I will share my screen. So the beautiful thing is, it did the cyclovoltammetry, it put the data into the cloud, and it also, I have first scan here, I've got second scan here. It's even processed the data for me. So you don't have to code this. It's actually given me micromolar. Suddenly you've gone from a cyclovoltammogram to final concentration super quickly. And the reason being is because this is Julie. This is a cloud or data management system from Zimmer Peacock. This is what that app has sent the data to. If I look into my tools here, I've actually said to it, when that voltammetry comes in, I want you to first of all filter my data, because when you get real data from the real world, you know, there could be all sorts of noise in your data. So let's do what we call a low pass filter on it. Let's then look for the data. Go and look between, go and center around 250 millivolts, plus or minus 50 millivolts. So that's what that window, that means there. And let's look at that reverse scan. And let's fit it to this formula, because when I fit it to this formula, I'll be able to calculate what the concentration is. So please understand that most scientific papers finish at this point, where here's my first scan, here's my second scan, end of it. You may then describe how you actually are able to turn that concentration, sorry, that peak height into a concentration. You may be able to discuss that. But in fact, this database actually converts it into that concentration and sends the result back to actually the phone as well. So that is the summary of what we're talking about here. We're talking about an app making Bluetooth connection with some hardware. The hardware gives the data back to the app. The app sends the data to the cloud. You are not excluded from that data, but you can also train that cloud to actually convert that raw electrochemical signal into a concentration. And when you've done that and you send that data back to the app, then you have a product. And that's really when you can sort of create impact. So I might just stop sharing that for a second. I'll just do a quick camera change, which is here. And I might just do a quick, let's say, summary. So in summary, if you're interested in wearables, we are doing a wearables only demo or deminar. Oh, sorry, deminar. Deminar maybe is a new thing. Wearables only webinar on the 31st of July. Biggest thing that's holding up a lot of electrochemical biosensor development is actually those screen printed electrodes. Nobody's talking about that oversupply in the market, and it may be partly oversupply, but it also may be just that there's too many product configurations out there that are basically diluting anyone's one sale of a screen printed electrode. And I think people could find it frustrating. But if you come to Zimmer and Peacock, we will tell you, look, there's a limited number of screen printed electrodes you should be using. Why? Because actually we produce them in high volume, low price, high quality. This is a cloud-enabled potentiostat. This is a game changer. This now, no cables, not large, looks more like a flipping Apple device. It's even got nice capabilities of being able to take it apart to clean it and stuff like that. No slots, no cabling. This is an elegant little device. LEDs to guide that user experience. It looks more like a product than it does a scientific instrument. And to be honest, scientific instruments should be more professional these days in their appearance. I actually think that is a definite movement that's going on. It means that you can actually commercialize or go from technology readiness level number 3 to 9 much quicker. And I showed you a demo when actually it took the raw signal, it found the peak. Because I put into it, because I'd given a formula when I turned peak height into concentration, it just calculated me concentration straight away, and I could send that back to the smartphone. Suddenly, when you send it back to the smartphone, the doctor, the nurse, the environmentalist, the food technician, they're getting a number they understand as opposed to the voltammetry, which is holding back. It's that last step which is holding back a lot of translational science. And I realized I wasn't actually sharing any of my screen there when I was sort of saying all of that. But if you do have any questions regarding the technology from Zimmer Peacock, then don't hesitate to reach out to us. I appreciate I've actually been talking for 1 hour, 2 minutes. I slightly apologize for that. I'll send you a recording of this very shortly. And if you have any questions, you'll get my personal email very shortly anyway. So take care and have for me, it's a good evening. And for you, it might be a good rest of the day. Okay, take care.